Lord Kelvin's quotation, "To measure is to know," was made in the days of the micrometer and the vernier caliper. The vernier caliper has recently been digitized using the precision of printed circuit manufacture to produce an accuracy of plus or minus 0.01 of a millimeter. This is good enough for a large percentage of everyday measuring. Because of the need to conserve the battery, the signals coming from these devices are only 1.5 volts and they are not suitable for input to a computer, which typically requires 3 to 5 volts. In traditional computer numerical control, the controlling computer needs to know after every measurable movement of the tool on the workpiece. This is required to provide the feedback loop that controls the future movement of the tool on the workpiece. The positioning is now often performed by the computer-controlled stepper motors, which advance the tool by a predetermined amount. The production process still has to ensure that the theoretical position corresponds with the actual position. In handcraft-controlled work, the position must also be checked, especially when approaching the final cut. In these applications and in quality control for computer capture of actual sizes, the fact that the caliper gives only 8 readings per second is not a disadvantage. Why not 100 times per second? Or 1,000 times a second? Sending signals takes battery power, shortening the expensive battery life. There is no need to send any signals if the value does not change. If it does change, then it takes at least 1/8 of a second to read the display, and it probably takes that long to ensure that the mechanical resonances of the tool and workpiece have settled enough to provide an accurate measurement. The caliper has 4 wires which I have soldered to a reasonably short flexible cable. These are connected to circuit mounted on the machine tool. The circuit has the power supply to replace the button cell in the caliper. This also converts the signal from 0 to 1 volts to 0 to 5 volts, allowing the driving of the signal through 10 plus meters of telephone-type cable to the remote reading station. The remote reading station could be a Raspberry Pi reading many calipers to a local database, or a PC. The still rapid signals from the caliper need to be handled by a real-time capable computer. I have used a 5-volt Arduino Pro to perform this task, and to display the readings on a cheap Chinese-built LCD. The long green flash of the Arduino signifies that the reading has changed. The short flash means no change has occurred. The oscilloscope reading shows the clock signal coming from the caliper. The op-amp circuit amplifies the clock and data signals from the caliper and provides the power to drive the signal the long way to the remote reading station, the Arduino in this case. The op-amp chip is powered by the remote station down the wire. The battery could also be replaced by the power from the remote station, but the standard AA 1.5-volt battery is economical compared with the button cell. Here is the code I wrote for the application, which I have given to you free under a Creative Commons license. Enjoy any fun you have building this useful and instructive project. If you discover any connector that couples with the caliper that does not cost as much as the caliper, please let me know. If you cannot measure it, you cannot improve it, said Lord Kelvin.